Welcome to AI Paperslop. If you are building an AI agent right now, you are probably explicitly telling it to summarize past conversations, to save on API costs and context window limits.
Yeah, that is pretty much the standard industry practice at this point.
Right. But according to a massive new evaluation of agent memory systems, doing that is actually destroying your agent's ability to reason. It drops its factual recall by almost 3 times.
It is a brutal finding, honestly.
So today we are looking at the paper. Are we ready for an agent-native memory system by Wei Zhu and a team from Shanghai Jiaotong, Tsinghua, and MenTensor?
And it is a really comprehensive study.
Yeah, so here is the rapid-fire summary for the ML engineers and researchers tuning in. This paper evaluates 12 different LLM agent memory systems across 11 datasets.
And it demands we stop treating agent memory as a black box NLP trick. We have to start evaluating it as a rigorous modular data management system.
Exactly. The TLDR is that there is no universal best architecture. Flat vector array fails catastrophically over long horizons, and raw text retention actually beats abstractive summaries.
Yeah, and graph and tree structures completely dominate for scattered temporal reasoning. But they come with massive computational overhead compared to localized update systems.
So the ultimate takeaway is that your pipeline design and your data structure matter far more than just swapping in a stronger LLM backbone.
It really is a massive wake-up call for the AI engineering community. I mean, the core issue this paper exposes is how deeply flawed our current evaluation methods are.
Oh, totally. We've just been looking at the final output.
Right. For too long, you and I, and really everyone building agents, have been evaluating memory end-to-end based purely on whether the agent gets the final answer right.
Yeah, we look at a benchmark, check the F1 scores, which just measure word overlap or exact match metrics, and we treat the whole system as a monolith.
Exactly. Which means we've been completely ignoring the infrastructure underneath. If you've ever watched your agent confidently hallucinate a user preference that you know is sitting right there in your vector database, well, this is why.
It's like evaluating an operating system based purely on whether the UI looks nice while completely ignoring how it allocates RAM or writes to the hard drive.
That is a perfect analogy. So to move past that surface-level evaluation, the authors propose an analytical framework that breaks agent memory down into a 4-module taxonomy.
Okay, what are the 4 modules?
First, you have representation and storage, so how data is logically structured and physically saved. Then, extraction, how raw interaction traces are processed before they hit the database.
Right, the ingestion part.
Yeah. Then retrieval and routing, how the agent actually finds and pieces together that scattered info. And finally, maintenance, how the system updates, compresses, or forgets information over time.
So when you break it down like that, you hit the paper's first major finding, right? That no single memory architecture wins everywhere.
Precisely. It depends entirely on the bottleneck of your specific workload.
Let's make that concrete for the listeners. So the paper highlights different benchmarks where different architectures shine. For example, structure-aware systems, things like ZEP and Cogni that build temporal knowledge graphs, they absolutely dominate on cross-session tasks.
They do. The long meme-evil benchmark proves this. When your agent needs to connect facts that are scattered across days or weeks of interaction, graph structures win.
Because they explicitly map relationships between entities. Like, if I mention a dietary restriction on Tuesday and ask for a restaurant 3 weeks later.
Exactly. But if you look at a benchmark like Locomo, which tests exact grounding in long dialogues, hybrid filtering systems like Memos take the lead.
Grounding meaning, like, pulling a highly specific date or granular detail out of a massive wall of text.
Right. MemOS uses a course-defined routing strategy to isolate the exact text span, so it wins there.
Okay, but there's a third scenario of the paper test that I think is the most relevant for anyone building autonomous agents, and that's stateful execution.
Yes, the DB benchmark.
Right, which evaluates whether an agent can execute procedural database operations. And here, systems that just preserve the raw chronological trace, like long context memory, win outright.
It is super interesting. Let's think about how procedural operations work. If I tell an agent, book a flight to Paris, and then 10 minutes later say, actually cancel that and book London, the agent's memory undergoes a state change.
Yeah, the reality of the situation updated.
Right. And if you evaluate that agent using an exact match metric, you are essentially just asking, did the agent output the word London?
Which is fine for a single static fact, But dbbench is testing if the agent can execute dependent operations in the correct order.
Exactly. It doesn't matter if the agent can parrot back a destination string if it fails to apply an update operation before an insert operation in the backend.
It has to understand the sequence of events. If it just searches its memory for flight destination, it might pull up Paris and London simultaneously.
And it won't know which one is the current reality. When correctness depends on intermediate state changes, finding a lexical match just isn't enough.
You have to preserve the chronological interaction traces so the agent understands the timeline.
Right. So knowing that different architectures solve different problems, let's follow the life cycle of a piece of data to understand how to build this properly.
Okay, let's start with ingestion, how the data gets into the system. And I really want to challenge the paper's findings here, because they contradict almost every tutorial published in the last 2 years.
Oh, they definitely do.
Every guide tells ML engineers to have their agent summarize past context. The logic is obvious. You summarize to save tokens, reduce API costs, and cut down on noise.
Yeah, that is the conventional wisdom.
Right. Like if a user spends 10 turns arguing with the agent about a formatting error, I don't want that garbage in my database. I just want the final formatted code. But this paper explicitly says summarizing is a terrible idea. Why?
The answer lies in the ablation study they ran on the LightMem system, which isolates the extraction module. They compared 2 variants.
Okay, what were they?
One was a user-only raw variant, which keeps the verbatim text of what the user said. The other was a user-only summary variant, which uses an LLM to rewrite the session into a concise summary before saving it.
So raw chat logs versus a clean summary.
Yes. And on the Locomo benchmark, which tests that exact factual grounding we talked about, the raw variant achieved a score of 24.2.
Okay. And the summary?
The summary variant plummeted to 8.5.
Wow. That is a nearly 3 times reduction in exact factual recall just because the text was nummerized.
It gets worse. Even light compression, where you just tell the model to remove filler words but keep the core facts, severely hurts exact detail recovery on the long evil benchmark.
So any alteration is destructive.
Exactly. The authors call this the late filtering principle. Aggressively extracting or summarizing data at right time destroys the agent's combinatorial reasoning.
I want to make sure I understand the mechanics of that. When you say combinatorial reasoning, you mean the agent's ability to connect seemingly unrelated dots later on, right?
That's right. When you force an LLM to summarize a session, you are forcing it to decide what is important in that specific moment.
Oh, I see. But the definition of what is important changes over time.
Exactly. In complex, long-term interactions, a weird, seemingly irrelevant detail mentioned in session, one might only become relevant 30 sessions later.
Like a user complaining that a specific software dependency always crashes their machine.
Yes. If they ask the agent to write a deployment script months later, and you abstracted that complaint away to save 20 tokens, the context is permanently destroyed.
Okay, I hear you, but let me push back as an engineer managing a production database.
Yeah.
If I don't use fine-grained LLM extraction to summarize, my vector database is just going to be a million chunks of raw chat logs.
Well, it's...
I mean, bums, ahs, failed tool calls, typos. How is the agent supposed to find anything in that garbage dump without hallucinating?
The paper doesn't advocate for chaotic dumping, though. It advocates for coarse segmentation. Look at how the MemoChat system handles this.
How does it do it?
It uses a heuristic topic segmentation. Now, heuristic in this context means it uses rules-based splitting, like segmenting by time gaps or after a certain number of speaker turns.
So it's not asking an LLM to actively read and rewrite the text.
Right. This rule-based grouping keeps related conversational cues together in their original verbatim state. It preserves the specific phrasing and the back-and-forth context.
Because if you extract entities too aggressively, you strip away the connective tissue the model needs to understand why a fact is true.
Exactly. So we are saving all this raw, messy chat history to preserve that tissue. But that naturally leads us to the next massive bottleneck.
Right. If we have this giant, uncompressed database of verbatim conversations, how does the agent actually find the right information? We are moving into the retrieval and reading phase.
Which is where standard RAG pipelines really show their limits.
Yeah, because in standard RAG, we usually evaluate success based on recall at 1. Did the system find the single most relevant chunk of text on its first try?
Right.
Standard RAG is like looking for a specific page in an encyclopedia. You type a query, it finds the page with the most semantic overlap, and you're done.
But agent memory, as this paper shows, is entirely different.
It's more like trying to piece together a torn-up treasure map scattered across a whole library. You don't just need one page. You need 6 different torn pieces from 6 different books to see the whole map.
That is a highly accurate way to visualize finding 2. The authors tested how accurately these memory systems surface stored evidence over time.
And what did they find?
They found that a system like SimpleMem is fantastic at recall at 1. If you just asked about a dietary restriction yesterday, SimpleMem will nail it.
What happens when the gap gets wider?
Exactly. The researchers measured the evidence distance gap. This is the temporal distance between the query being asked in, say, session 31 and the supporting evidence buried way back in session 1.
And as that gap widens, flat similarity search, which is the dense vector search standard R uses, just falls off a cliff.
It really does.
Let me unpack why that happens technically for the listeners. Dense vector search embeds text into mathematical space based on semantic vibes or general meaning.
Right, the embedding vectors.
So if a user talks about a project architecture 30 days ago and then talks about project architecture again yesterday in a totally different context, the search gets confused.
Yeah, a naive dense vector search will see both of those chunks as highly similar to the query.
It blends the semantic meaning, causing the old critical detail to get buried under a mountain of subtly shifting, more recent distractors.
Exactly. Flat semantic similarity degrades over time and distance. But systems like AMEM and memtree completely dominate when you look at recall at 10 over those long distances.
So they are pulling up 10 chunks and actually finding the right pieces.
Yeah, AMEM maintains an 85.9% recall at depth 10, whereas the standard embedding arg baseline drops sharply.
Walk me through the mechanics of memtree and AMEM. How do they actually survive that distance gap when standard RAG fails?
They survive because they organize memory as a structured evidence space, not a flat similarity cache.
Okay, so memtree, I'm guessing by the name, builds a tree.
Yes, a hierarchical tree structure. The raw conversations are the leaves, and as you move up the branches, it creates intermediate summary nodes that group themes together.
So when the agent queries a memory, it doesn't just scan the leaves.
Right, it navigates down the branches logically. AMEM takes a different approach using explicit relation-aware routing. It maps how different memory chunks relate to each other.
So when the required evidence is scattered, retrieval is no longer a top-1 ranking problem. It is an evidence completion problem.
Exactly. You need an explicitly organized structure to gather piece A, follow a relational link to piece B, and aggregate them.
What about the actual search query itself? When the agent goes looking for piece A and piece B, how does it construct that search?
That brings us to finding 8, which focuses on the routing mechanics. The most effective systems explicitly plan the query before searching.
And they use modern hybrid fusion, right?
Yes, they do.
Just to clarify for the audience, hybrid fusion usually means combining dense vector search for the semantic vibe with sparse search, like BM25, which looks for exact keyword overlap.
Correct. AMEM uses a balanced fusion of both. The dense search catches semantically related concepts, while the sparse search catches exact idiosyncratic terminology.
Like a highly specific error code the user mentioned weeks ago.
Exactly. But the real performance boost comes from the explicit planning. Having the LLM decompose a complex user intent into multiple distinct subqueries before it even touches the database consistently improves results.
But here's where the paper gets really counterintuitive. We usually assume that giving an LLM more time to think improves performance.
Yeah, the whole chain of thought paradigm.
Right. But the researchers note that if you add an extra reflection step to the routing, so the pipeline is planning plus reflection, it actually hurts performance.
Why? The SimpleMem ablation study isolated this. They found that a planning-only approach yielded higher accuracy than planning plus reflect.
That is so weird. Why would thinking about the search query twice make it worse?
Mechanically, it seems that once the LLM establishes a solid logical route to the data, adding an extra layer of reflection introduces unnecessary computational overhead.
And it second guesses itself.
Yes. It often prompts the model to overcomplicate the search query with constraints that cause the database to return 0 results.
Overthinking the search query. I mean, we've all been there when fighting with Google.
Oh, absolutely.
Okay, so let's summarize where we are. We've ingested the raw, messy data without destroying its combinatorial potential through early summarization.
Right.
We've built a structured, hierarchical, or relational database to find the scattered pieces of our treasure map. Now we hit the final hurdle.
And honestly, the one that governs whether an agent is actually production ready.
Maintenance over time. What happens when facts change? What happens when an agent runs continuously for 6 months?
This is the hardest part.
Let me ask a pragmatic engineering question. Instead of building complex graph databases or tree structures to handle conflicting facts, can't I just throw a smarter, bigger model at the problem?
It is a tempting thought.
I mean, if I upgrade my agent's brain from an 8 billion parameter model to something massive like GPT 5.4, won't its native reasoning just figure out which memory is the most recent?
The paper's ablation on LLM backbones finding 3 proves that assumption completely false.
Really?
Yeah. The researchers ran the exact same memory pipelines using 4 different models: Qwen 3.8b, DeepSeek Chat, GPT 5.4 Money, and the full GPT 5.4.
And what happened?
Well, upgrading the model backbone definitely improves the phrasing and the realization of the final answer. Your answer F1 score goes up simply because a frontier model writes more fluently.
But let me guess, the actual underlying facts don't improve.
The stability and the temporal grounding remain heavily dictated by the memory pipeline, not the LLM's parameter count. The model acts as the renderer, but the pipeline is the source of truth.
So a better model just hallucinates more eloquently if the pipeline is bad.
Exactly. For date-grounded, latest state queries on the Locomo benchmark, the MEMOS pipeline remained factually correct across all 4 LLM backbones.
While the embedding array Brug pipeline remained fundamentally broken across all 4.
Yes. If you feed a frontier model stale, conflicting context without explicit temporal structure, it will still hallucinate the past. You cannot brute force it with model capacity.
So how do you solve the maintenance problem? If you have 2 contradictory facts in your uncompressed database, say user lives in Paris from January and user lives in London from July.
Right. How does the system manage that state without breaking? Finding 9 tackles this directly. The winning strategy is called conservative consolidation.
What does that actually look like in practice?
Well, the researchers looked closely at how the MemoryOS system handles updates. If a system uses delayed flushing, meaning it lets new contradictory evidence sit unresolved in a short-term buffer for too long, the memory fragments.
Because at query time, the agent doesn't know which fact is active.
Exactly. And on the flip side, if a system uses overly coarse summarization during the update, it obscures the timeline.
So conservative consolidation is the middle ground.
Yes. It selectively merges related facts while preserving the cross-turn linkages. It maintains multi-version chains.
Oh, that sounds exactly like Git version control for code.
That's a great way to think about it.
You don't delete the old file or overwrite it completely. You append a new commit that updates the state, keeping the history intact so the system always understands the timeline. You don't delete Paris, you just invalidate it via timestamp and add London.
Exactly. You are appending state changes rather than destructively overwriting facts. But this brings us to the elephant in the room.
Cost.
Yes, finding 5. Cost and latency. Maintaining a multi-version temporal knowledge graph or a hierarchical tree requires massive compute.
Right, because every time a new fact comes in, the system has to figure out where it belongs in the graph, draw new edges, update timestamps.
And maybe re-summarize a branch. The operational costs are staggering if you aren't careful. The researchers measured the utility latency trade-off, and it's a massive reality check.
Walk me through the actual numbers. How bad is the latency?
Highly structured systems, the ones that rely on graph-wide consolidation and global refreshes, like Cogni or MemoryOS, scale terribly. On the long bench workload, MemoryOS took an average of 490 seconds of operation latency per query.
490 seconds. That is over 8 minutes per query.
Yeah, it's wild.
You cannot build the production user-facing agent with an 8-minute latency. The user will think the app crashed and close the window.
You absolutely cannot. Cogni exceeded 116 seconds, which is still completely unviable for real-time chat.
But what about the other systems?
Well, then you look at the LightMem system. LightMem uses localized updates rather than global reorganization. Only took 17 seconds.
Okay, 17 seconds is still substantial if you're waiting for a text message reply, but it's in a completely different universe than 490 seconds.
Exactly. Finding 5 establishes what we can call the operational scaling rule. Efficiency is governed by maintenance scope.
Meaning you only update what you absolutely have to.
Right. Bounded hybrid retrieval and segmented compression keep LightMem relatively fast. Similarly, memtree uses path-local tree aggregation.
So when a new memory comes in, it only updates the specific branches of the tree that changed.
Avoiding a global refresh of the entire memory structure, isolating your update compute is the only way to build a sustainable system.
Wow. Okay, so to synthesize the ultimate playbook for the ML engineers and researchers tuning in today, First, do not blindly compress your inputs to save tokens.
Preserve the raw, verbatim context through rule-based heuristic segmentation.
Right, because late filtering is essential for complex combinatorial reasoning later on. Second, ditch flat vector exe for cross-session reasoning.
You need graph or tree structures to bridge wide temporal gaps.
Exactly, to explicitly link scattered evidence. And third, hyper-optimize your maintenance module for localized updates, because global graph refreshes will cause your latency to spike to 8 minutes.
And your API bills to bankrupt you. That is the architectural blueprint for building a resilient, agent-native memory system today.
It's a fundamental shift in how we build. But I want to leave everyone with a final forward-looking thought, something to mull over that isn't explicitly answered in the paper.
Oh, I like where this is going.
As frontier models rapidly push toward infinite, natively cached context windows, we are talking millions, potentially tens of millions of tokens in a single active prompt. Will the future of agent-native memory shift away from external databases entirely?
That is the million-dollar question.
Maybe the memory architectures of tomorrow won't be about storing, fetching, and updating data in vector or graph databases at all. Maybe they will be purely about algorithmic indexers that just point the LLM's attention heads to the exact right part of its own massive, persistent, active context. Until next time, keep building.